Good morning, everyone.
Good morning.
Good morning. On Tuesday, we covered section 4.4, solving exponential equations and logarithmic equations. And today we are going to cover the last section of Unit 4. We are going to look at exponential modeling. In Foundation 2, you should have learned linear modeling, right? Use a linear function to simulate the real life problem. And this section, we are going to use exponential function, either exponential growth function or exponential decay function to explain the real life problem. So we only have 3 questions on my guided note. So let's spend time to work on it. Once we finish the 3 questions, we are going to start a review for Unit 4 test. That's the plan for today. Let's look at the first question. The half-life of radium-226 is 1,590 years. If a sample contains 400 milligrams, how many milligrams will remain after 4,000 years? 4,000 years. Okay, so give your answer accurate to at least 2 decimal places. The last sentence is about a rounding instruction. All right. Sometimes the problems give us the formula. Then we have to use the formula or the equation that is provided. Sometimes the questions like this problem does not provide any equations or function. Then this is the function you are going to apply, okay? The formula, it is P equals P sub 0 times E to the power of RT. Let me explain the meanings of those variables in this formula. This is the function that can do the exponential model. Okay, when we do the linear model, the function is y equals mx plus b, a straight line, right? And if we do exponential model, and the function we are going to use is p equals p sub 0 e to the power of rt. Let me explain the meaning. P sub 0 is the initial value of the dependent variable. In this case, would it be the weight of the substance, right? So P sub 0 is the initial value. Initial value of y, or of the function, We know E is the Euler number, right? Around equals to 2.7. And R is the rate. Normally it will tell you T here is time. And P here is the function. P equals P sub 0 times E to the power of RT. RT here is on the shoulder of E. All right, so the problem mentioned half-life. What is half-life? What does half-life mean? Half-life is the time that it takes for the substance to reduce half of the weight. let's say originally the sample is 400 milligrams. Half-life is 1,590 years. That means it's going to take 1,590 years for the substance to decay to 200 milligrams. So that is the meaning or explanation of half-life. Okay, half-life is not like my life expectation is 80 years old, so half-life is 40 years old. No, that doesn't work like that. Half-life is the time it takes for the substance to decay, to lose the weight, right? To decay as to a certain point, whose weight is half of the initial weight. Half of the initial weight. Okay, let's see how do we use the first sentence to find some information. The half-life is 1,590 years. So we can do this. Half-life. When t equals, like in 1,590 years, when t equals 1,590, the weight of the substance P would be, sorry, half of P sub 0, okay? P sub 0 is the initial weight of the substance, initial value of the function. Right here, I had the exponential of P sub 0. P sub 0 is the initial weight of the substance. So in 1,590 years, that's the half-life of the substance, right? And the weight would become half of the initial weight. So half P sub 0, okay? And then times e to the power of RT. T is 1590. As you can see, so far, by the way, E is a constant, okay? E is a constant. It's not a variable. Is known. The value is known. So in this equation, after we use the first sentence, after we use that information, we have this equation set up. And notice on the left side and the right side of the equation, we have a P sub 0. If we divide both sides by P sub 0, we could get rid of P sub 0 from each side, right? And after that, we should only have 1/2 equals e to the power r times 1590. Means the equation now only can turn one unknown. The unknown is r. So we can calculate the value of r. So the first sentence actually gives us a way to find the value for r. R is the rate. R is the rate. Okay, so let's see how do we find the value for r. R is the unknown, right? The unknown appears in the exponent. So the equation we are looking at right now, this equation we are looking at right now is an exponential equation. On Tuesday, we covered exponential equation, right? We have learned two methods to solve exponential equations. For this problem, for this equation, we're going to use the second method. We are going to apply ln on both sides. We are going to apply ln on both sides. And then the left side, we have ln half. Yeah, we can keep half, that's no problem. But if you want to play with it, you can write half as 2 to the power of -1, and then move the -1 in front of ln 2. Is negative ln 2. But if you keep ln of half, is totally fine, okay? It's totally fine. On the right side, excuse me. On the right side, we have ln e to the power. I feel more comfortable with the constant in front of the variable, so I'm going to write 1590 r. Okay, this way. It's the same thing. 3 times 2 equals 2 times 3. Commutative property. And the right side is a log with base e, so it's a natural log, right? And the argument is the yellow part, and the argument is a power. So we are able to apply the power rule to refresh your memory. Let's remember what's the formula for power rule. LG with base b x12r It's not that R, by the way. Is the formula. We can use alpha. We can change a different notation. And then the exponent in the argument can be moved in front of the log. Okay, so we have alpha times log with base bx. Okay, so remember that's the power rule. So we are able to move this exponent in front of the log. And let's see what happened after that. Left side ln half. Right side, we move the exponent 1590r in front of the log e. Not log e, natural log e. Anybody can tell me the value of ln e? Anybody can tell me the value for ln e?
1.
Exactly, awesome. ln e is a natural logarithm with base e and the argument also is e. When we have a log whose base and argument are identical, then the log is equals 1. So this part is 1. We can just get rid of it, right, in a multiplication. And now we have ln half equals 1, 5. Okay, we have that. We have ln half equals 1590r. And then to find the value for r, we divide each side by 1590. 1590. And then r is isolated on the right side. And we have r equals ln half over 1590. You know, I'm not going to use the calculator to figure out what's the value of r, because it's very likely is a irrational number, you know, ln half. Yeah, so we're gonna have we're gonna have to round the decimal. So I don't want to do that. I want to keep the value of r exactly what it is. So I'm gonna write r, keep r as ln half over 1590. Okay, so we have the r found. We have the r found. Not done yet, guys. This is a long process. Long process. So based on the first given information, the first sentence, the half-life of the whatever it is, the substance is 1590 years. Based on that piece of information, we got the value for rate. Value for rate. Okay. By the way, this rate is negative. It makes sense because it's exponential decay, right? In the substance in the nature, they eventually, you know, is decaying. Why do we know is a negative? Because ln half is ln 2 to the power of 91 is negative ln 2. So if we have a log, both the base and the argument bigger than 1, then the log is positive. So ln 2 is positive. So with the negative sign in front of it, it is a negative. So the numerator is negative, the denominator is positive, r is negative. Well, that makes sense because r is negative, because we are looking at a exponential decay problem. Okay, let's keep reading. Let's see what we can. Let's see what do we need to do for this problem. If a sample contains 400 milligrams, that could be the p sub 0, right? Yeah, the initial time when you start to do the research, when you start to look at a substance, that is p sub 0. How many milligrams will remain after 4,000 years? That is t. T equals 4,000. All right. So let's use the formula that I gave you earlier. P equals P sub 0 e to the power RT. P is we're going to find out, you know, what's the weight of that sample after 4,000 years. So P is the, you know, P is the weight of the substance, right? Is the dependent variable. The weight of the substance depends on the time. Depends on the time. Over time, the substance is losing weight. Depends on the time. So we are looking for the value of P when T is 4,000. When T is 4,000. And the P sub 0 is 400 milligrams. E is constant again, is constant. R is also a constant for a specific substance. How fast it decays is an objective existence, is a constant. And the constant rate we have already figured out is right here, right? Is right here. Let me keep that as R for now, because if I plug in, it's going to be very troublesome. So I'm going to just keep R here. Is known because we have already found the value for R is right here, all right? And the T is 4,000. 4,000. As you can see, all the value to the right are known, right? We are looking for P, and initial value is 400 milligrams. Yeah, E is also a constant. R is the constant that we already found the value earlier, and the T is 4,000. So we just need to, plug in everything. Is that 400? Yeah, 4,000. Okay. So now let's see if we can put this R back. 400 E, R is ln half over 1,590, and then times 4,000. So I'm gonna times the 4,000 on the top, all right? Yeah, this is again is algebra. So when we go up higher in mathematics classes, the concept is more abstract, yeah, more intricate, but mainly, in my opinion, that actually challenging some of the students is the algebra part. So now we're just plugging in R, and since R times 4,000, I put the 4,000 in the numerator. I think I'm gonna just enter this expression in a calculator. If you could write this expression down or take a screenshot, I'm gonna take a screenshot because the Zoom does not support sharing the whole desk. You can only share one app at a time. I'm gonna use my TID for calculator. I just took a screenshot, take a picture of the expression we are going to evaluate. So I'm gonna stop share the note and go to share my calculator. Okay, I have to turn on my calculator first. Open the app. Let me share the calculator. Right here, okay. With a good calculator, would really help your exams. You can bring any calculator with you. Okay, so I assume you have the expression on your scratch paper, okay? We start with 400. Remember the initial weight of the substance of the sample is 400 milligrams. So 400 times, you don't have to enter this one, okay? If you enter, that's fine. You don't have to, the calculator know you are multiplying. 400 and E, do you see ln? ln here, and the top left, on the left shoulder is e to the power of x, right? So we're gonna do second ln. We set up the exponential function with base e. And then the exponent is very complicated. Some of you might need to use a parentheses, extra parentheses, depends on your calculator. If even both of your calculators are TID4, it might vary, like details a little bit different. So since my emulator raised the exponent on shoulder of e, I do not need the extra parentheses to frame the exponent. So I'm gonna just enter the ln half 1 divided by 2, close the argument, and then multiply that by 4,000, right? As you can see, the exponent stay on the shoulder, up high on the shoulder of e, and then divided by 1,590, like that, all right? Let's see what we have. After 4,000 years, what is the weight? Is around equal to 69 or 60 or 70 milligrams. Let's see how do we round it. The question requires to round it to 2 decimal places. Okay, 2 decimal places. So 69.94, because this digit 4 is less than 5, so we round it down. The answer is 69.94. Let me write it down on a note. 69.94, around equal to. All right. So I like to play with the calculator, play with the parentheses. Correctly use the parentheses actually indicate you are really clear about the structure of the expression. For example, I can do this one. 400 e to the power, I can use this parenthesis as to frame the whole exponent, all right? And I know my exponent is a quotient, so I'm gonna start another parenthesis to frame the numerator, which is ln half, right, times 4,000. So that's the numerator. This parenthesis frame the numerator of the exponent, and then divided by the denominator 1,590, and then close the parentheses that frame the whole exponent. Yeah, I like to play with those parentheses. That means you understand the structure very well. Also, I'm not sure earlier because every calculator is different, right? So when you play the more, you get more familiar with your calculator. And when you take the test, your calculator will be able to help you. So that's this problem. Let me stop share the calculator and then go back our note. Our note is here. Do you guys have any questions? As I mentioned, some questions give you an equation or a function and requires you or ask you to use that function to solve the problem. Then do not use this one and use the one that is given. But if the question does not provide any function, just say is an exponential model, then you can use this formula, guys. All right, I put it in red. P equals P sub 0 times e to the power of RT. P sub 0 is the initial value of the function. R here is the rate. When R is positive, it's exponential growth. When R is negative, in this case, exponential decay. T is the time. T is the time. All right. If you have ever took, I think foundation 2 have compound interest, and that formula actually is the continuous compound interest formula. Yeah, but we can use that for the exponential model here. Do you guys have any questions? If we think about, let's make sense of the half-life. 1590, okay? Yeah. 1590 is half-life, means after 1590 years, 1590 years, the substance should weigh 200 milligrams, right? And another 1590 years, and that's gonna be times 2, 8, 31. After 3080 years, it's gonna be 100 milligrams, right? Yeah. And then if another, so it makes sense. After 3180 years is 100 milligrams. Then after 4000 years is around equal to 70 milligrams. That makes perfect sense, right? I think the answer is very reasonable. I think this is a correct answer. Any questions, guys? Are you guys still there?
Yes, we just don't have any questions.
Oh, okay. Then let's move to the next problem. Question number 2. The half-life, yeah, again, half-life. The half-life of a P100 is for, I learned chemistry in my own language, so I don't really know how to pronounce those terminology. I apologize that. So the half-life of P100 is 4 days. After 16 days, a sample of the substance has been reduced to a mass of 4 milligrams. What was the initial mass of the sample? Okay. What is the mass in milligrams 8 weeks after the start? You may enter the exact value or round it to 4 decimal places. Okay. Similar, right? Is also a decay problem. It's also an exponential decay problem. The half-life is 4 days. After 16 days, okay, how about let's just use the meaning of the half-life to figure the first part of the problem, okay? So the initial, this is start point, starting here, okay? What's the mass, the initial? We don't know. That's what we're trying to figure out, right? And half-life is 4 days. Half-life is 4 days. How about we use x here? Initial value is x. After 4 days, it should be half x, right? After another 4 days, that's gonna be after this way. After 8 days, it's gonna be a quarter of x, right? And after another 4 days, and now it's gonna be 12 days, is divided by 2 again, so 1/8x. And after another 4 days, which is 16 days, we have 1/16x, right? Does that make sense, everybody? So every 4 days, half-life, every 4 days, the weight cut in half. So after 4 days, half x. Another 4 days, a quarter x. Another 4 days, 1/8x. Another 4 days, 1/16x. And after 16 days, it says after 16 days, the sample weights, the sample has the weight of the sample has been reduced to a mass of 4 milligrams. That means 1/16x is a 4 milligram. Okay, and this gives us a simple equation. And we can solve the equation. 1/16x equals 4. Multiply by 16, multiply by 16, cancel, x equals 64. So the initial weight, what was the initial mass of the sample? It is 64 milligram, all right? 64. You don't have to write milligram because it already specified in milligrams. That's the first part. How do we use the meaning of half-life to figure out the initial mass of the sample? 64 milligrams. Part B, what is the second part? What is the mass in milligram 8 weeks after the start? 8 weeks. A week has 7 days. So 8 weeks is 56 days, right? 56 days. And you know, we could keep going doing the same thing if you like. So that is 16 days is 4 milligrams. After 20 days, yeah, after 20 days is gonna be 2 milligrams, right? After 24 days, it's gonna be 1 milligrams. After 28 days, half. After 32 days, every 4 days, cut in half. After 36 days, after 40 days, after 44 days, after 48 days, divide by 2. So the denominator is doubled. After 52 days, 128, right? Divided by 2. So 2 times 64 is 128. After 56 days, 128 times 2, 256 milligrams. Right? We don't need to use a formula or anything, and it works. Just use the meaning of the half-life. So after 56 days, that is 8 weeks, the weight or the mass of the sample is going to be 1/256, that much milligrams. All right, that's the second problem. Yeah, we did not use the formula. Instead, we used the half-life. Isn't too bad, right? Isn't too bad. Question number 3. You go to the doctor and he gives you 15 milligrams of radioactive dye. After 24 minutes, 7.25 milligrams of dye remain in your system. To leave the doctor's office, you must pass through a radiation detector without sounding the alarm. If the detector will sound the alarm, if more than, what does the if means here? If more than 2 milligrams of the dye are in your system, how long will your visit to the doctor take? Assuming you were given the dye as soon as you arrived. Oh, so complicated. Give your answer to the nearest minute. So you will spend how many minutes at the doctor's office? Then when you leave the office, the dye in your system. Yeah, what's the standard? To pass the detector, if the detector will sound the alarm if more than 2 milligrams in your system, right? So we want less than 2 milligrams in your system. Okay, then you leave the doctor's office, right? So that's the goal. That's the goal, to pass the detector. The goal is to stay enough time in the office such that the the dye in your system is less than 2 milligrams. All right. So this is also a decay problem. I don't see any exponential growth problem. Let's see if we have some in the guided note. Okay, so the formula is going to be this one. P equals P sub 0 E RT, right? So the P is after the time you spend in the doctor's office, the how many milligram of the dye in your system. Okay, so initial value of P sub 0, the doctor's office will give you 15 milligrams of the substance. Okay, and E to the power of R T. We have 20 minutes. How do we understand this information, this piece of information? We do not know R, right? So the first piece of information actually gives us the way to find the value of R. Same with earlier. After 25 minutes, 7.25. That's the P, okay? Let me write a formula. After 24 minutes, 7.25 milligrams remain in your system. Initially, the doctor give you 15. Oh, it's not half. It's not 7.5, 7.25. And E to the power of R, T is 24 minutes. As you can see, with that information, the first sentence that is given, you go to the doctor office, they give you 15 milligrams of the substance. After 24 minutes, 7.25 milligrams left in your system. That information is for us to find the value for R. Very similar with the first problem we went over. And as you can see, this equation, R is the only unknown. So we're going to solve for R, okay? And firstly, I'm going to divide each side by 15 and cancel this 15. And we would have 7.25 over 15 equals e to the power of, I'm going to write r times 24 as 24r, right? And then we're going to solve this exponential equation. It is an exponential equation because the unknown is in the exponent at n, right? And we have at n 7.25 over 15 on the left side. And, you should be very familiar with this right now. On the right side, the argument of the natural log function has exponent 24r, and that exponent 24r by the power rule can be moved in front of the log function. So we have 24r times ln e, and we know ln e is 1, right? ln e is 1, so we're gonna get rid of it. So we have ln 7.25 over 15 equals 24r. We want to know the value of r, right? So divide each side by 24. And we have r equals ln 7.25 over 15. And then divide by 24. That is the rate. That is the rate. That is the rate. 7.25 over 15 is less than 1. Yeah, interesting about the log function is if both b and argument bigger than 1, the log is bigger than 0. If if the two value b and x, one is bigger than 1, the other is less than 1, then the log is less than 0. So we know the numerator, the argument is less than 1, but the base is bigger than 1. So I'm just to show you r is negative, okay? R is going to be negative, but we don't have to know that for the purpose of solving the problem. We have r found now. We have r found now. And what's the goal? The goal is to pass the detector, right? Detector. P equals P sub 0 e to the power of RT. And the initial value of the mass of the substance is 15. R is known right now, okay? R is known. And we want to know the T. We want to know how many minutes such that P, the amount of substance in your system, could be less than 2. We got an inequality. This is an inequality, okay? We want the remaining substance after t minutes less than 2. So we want to solve for t. Again, r is known. We found r earlier. We divide each side by 15. We have e to the power rt less than 2 over 15. And then we're going to take ln on each side. We can do so because natural log is an increasing function, okay? Natural log with base is e. E is bigger than 1, is 2.7, right? Bigger than 1, so it's increasing. That's the reason we can take ln. We can take ln. And after that, we have our t on the left side. I don't know if you see it, because this base can be brought in front of the log, and the log e is 1. So rt on the left side, on the right side, we have ln 2 over 15. Okay, and here is the challenging part. Here is the challenging part. It's just mathematics wise. To solve for t, to solve this inequality for t, we need to get rid of r, right? We need to get rid of r. But remember, r is less than 0. You don't have to know what exactly the value. Of course, if you enter this value, this expression in the calculator, you know the exact value, right? But the important thing is you need to know is negative, is less than 0, because obviously this is a decay problem, right? Decay problem, the rate always less than 0. Since to isolate t in the inequality right here, we need to divide each side by r, which is a negative number. We need to switch the direction of the inequality symbol. Okay, we need to switch the direction. Do you remember that from foundation 2? When we solve an inequality and we multiply or divide both sides of the inequality by a negative number, we have to switch the direction of the inequality symbol, okay? And the same thing, the right side, we divide it by r. Yeah, r is negative, so we have to switch the order of the inequality symbol in the middle. And r cancel r, we have t is bigger than ln 2/15 over r. Okay, now we can put the r back here. Now we can put the r here. R is ln 7.25 over 15 and then over 24, right? And you can try keep changing flip, and we're gonna flip the 24 on this top. So we have 24 ln 2/15 over ln 7.5 over 15. And that's the minute. At least you need to stay in the office that many minutes in order for the substance to go below 2 milligrams and you pass the detector. Do you need me to explain the quotient here? Okay, just very quickly. You have ln 2/15 divided by a fraction. The fraction has a numerator 7 ln 7.25 over 15, denominator 24, right? So we're gonna use the keep change flip. The fraction bar, numerator on the top, denominator on the bottom is division symbol. So numerator is ln 2/15 divided by the quotient ln 7.25 over 24, right? And 15 over 24. And then we do keep changing flip. If you remember that, keep the first fraction, we can do that as 1. Change division to multiplication and flip the numerator and denominator of the second fraction. So 24 on the top now, ln 7.25 over 15 on the bottom. So that's how do we have 24, here, and then times ln 2/15 all over ln 7.25 15. Okay. Now I'm going to take a picture of that expression since we are going to go to the calculator. I'm going to enter that expression exactly what it is in the calculator. Stop share the note and share the calculator. Okay. Yeah, as I said, I like to play. Well, make it maybe a little easier. How about we enter the numerator? The structure of the expression is just quotient, right? Let's do the numerator first. 24 times ln. Argument of the natural log is 2 divided by 15. Close the argument. So 24 times ln 2/15, that's the numerator. You enter, and that's the numerator. Use the numerator to divide by. Behind a slash, that's going to be our denominator. ln, start the argument, 7.5 divided by 15. Close the argument. Done. 69. Okay, 69.76, 69 minutes. So a little bit over 1 hour. That makes sense, right? If you go to the hospital or see a doctor, you leave like 1 hour. That's pretty reasonable time. Let's see how do we run it. You will spend how many minutes at the doctor's office? Give your answer to the nearest minute. Okay, the nearest minute, the nearest whole number. And that's gonna be 70 minutes. Okay, 70 minutes. Okay, let me double check. 24 ln 2/15. And divided by ln 7.5 over 15. Okay, that's correct. 70 minutes. Stop share this one and share my note. This one. You're gonna stay in the office 70 minutes. Right? Yeah, sometimes like if you are a very social person and you like to have a couple of drinks in a party and you also drive, you actually want to do the study to see how long for the alcohol to decay in your body to get out of your system for different type of alcohol drinks, you know. Yeah, you stay like in your friend's place after you drink, stay in your friend's place like a couple hours, and then you can drive, right? When the otherwise, if you get pulled over by the police, that's gonna be a very serious consequence. Do you guys have any questions?
I don't think so.
Okay, very good. All right. As I said, if we finish the 3 problems, we're going to start a review. Okay. Let me close this file. Save and close. And we're going to start a review. Let me share the review file. This one, study guide. Same with always. The questions on the study guide is highly similar with the actual problems you're going to encounter in the exam. In fact, there are a few, okay? A few are exactly the same problems because I couldn't find a very good like a sample problem from your homework. So I just leave exactly what it is from the exam. In order to prepare for unit 4 test, you try at least 5 times. Today we started. We won't be able to finish. Today is Thursday, and then next time Tuesday we finish, right? And after that, I'm gonna arrange your unit 4 test. To prepare for yourself, you need at least 5 times practice. Okay, let's get started. First question, solve exactly the given equation for x. What does that exactly mean? It's highlighted. Means you don't round it, right? You leave if you have ln or log, you just keep it. Okay, this is an exponential equation. The base on the left is 2, the base on the right is 11. We can write 11 to the power 1, right? So base is 11. And I don't see that it's convenient to write a 2 base as a power of the same base, okay? If 11 is 8, okay, I'm going to write 8 as 2 cubed. Then that's another different method. That's going to be the first method. Since we don't have that convenience, we are going to apply the second method. Second method, we are going to apply ln on each side, natural log, okay? Then on the left side, the log whose argument is a power. By the power rule, the exponent can be brought in front of the log. The formula log with base b x to the power r, the r can be brought in front of the log, r times log with base bx. So the left side is going to be x minus 3 times ln 2. Okay, don't forget to put a parenthesis to frame x minus 3 because that's one whole thing. Without parentheses, the structure is totally different, okay? And this means x minus 3, the whole thing times ln 2. But this means x minus the product of those two. So it's really different. They are very different. So be very careful. Do not make that mistake. On the right side, we have ln 11. Okay? On the left side, we have x minus 3 times ln 2. To remove the parentheses and isolate x, eventually we need to get rid of the parentheses. We need to apply the distributive property. If it feels better, if you we can actually distribute to the right, okay? The formula a plus b times c is a times c plus b times c, okay? And we have x times ln 2 minus 3 times ln 2. Give each member in the parentheses ln2, x times ln2, -3 times ln2. So the left side is x times ln2 minus 3 times ln2 equals right side ln11. Our goal is to isolate x, right? So now, knowing this is just a number, this is just a number. It looks complicated, but it's just a number. We want to get rid of the number. We plus 3 ln2 to each side. Cancel, right? Negative, positive, cancel. And the left side right now only have x ln2. The right side now we have ln11 plus 3 ln2, right? Almost there. ln2 is a number, again, it's a number. So it is the coefficient of x. So to isolate the x on the left side, we need to divide each side by ln2. ln2 cancel ln2 is 1. So on the left side we have x. On the right side we have ln11 plus 3 ln2 over ln2. You would have to enter that in the cell because it requires solve exactly the given equation for x. Means you're going to give the value of x, the solution, exactly the value. You don't round it. Okay, let me double check. Pretty straightforward, this problem. ln11 over ln. Oh, okay. Okay. Actually, there's one step we can process differently. Let me show you. 2 to the power of x minus 3 equals 11, right? There's one step we can handle it differently. So we apply ln, that's the same with earlier. And then we're going to bring x minus 3 in front, and ln2, and ln11, right? So here we could get rid of ln2 at this point, because ln2 is multiplied with x minus 3. We could get rid of ln2 at this point. ln2 cancel ln2. On the left side, we have x minus 3 only. This way, you don't need to distribute. On the right is ln11 over ln2. And then we add a 3 to each side. And then we have x equals ln11 over ln2 and then plus 3. Okay? Either way, it's the same. This answer is the same with this answer. It's the same thing. You enter this or enter this, the system will mark it as correct for both. All right, that's the first problem. Solve exponential equation. Solve an exponential equation with the second method. Question number 2, convert the exponential equations into logarithmic form. Okay. The formula, log with base b, x equal, not x, we do triangle and star. Star equals triangle, right? You know, b is the base, star is the argument, triangle is the log. Log is piece of wood, remember? A cabin, log cabin, a piece of wood. The base is going to carry the log on the shoulder and equals the argument. So those equations, two equations are equivalent. They are the same equation in two different formats. And so what do we have? The first part is 3 to the power of 5 equals 243, right? And we know 3 is going to be the base, no problem. 5 is the log, remember, a piece of wood, because 5 is on the shoulder, right? And 243 have to be the argument. We only have 3 things. So to convert to logarithmic form, we have log with base 3. Argument is on your scratch paper, right? Argument is 243 equals log 5, and done. That's the first part. Second part, the expression, the equation that is given is 0.01 equals 10 to the power of -2. Okay, 10 definitely is the base. 10 is the base. -2 on the shoulder of 10, right? And that's the log. base supposed to be on the bottom, on the ground. Supposed to put things on top of it, right? That's the reason it's called the base. And the -2 is on the shoulder of the base, so -2 is the log piece of wood. Then that would make 0.01 as the argument. And the logarithm form is going to be log with base 10, right? The 10 here. And argument 0.01 equals -2. And done. All right. Okay. Very important. It's not very, it is important to figure out that those are supposed to be aligned. The base is supposed to be go down, like a log 0.01. The base is supposed to be here, 92. So they should be on the same horizontal level, okay? Because I see a lot of students write the argument too way high, too up high. All right, so that is the second problem. I think this is a very basic. This is very straightforward. Question number 3. Solve exactly the given equation for x. This is a log equation, right? Log equation. We're gonna use the formula we have earlier. Log with base b star equals triangle is equivalent to b to the power triangle equals the star. Okay. In this equation, we have the base. Base is 2. Argument is 4x plus 6. Log is 4. So we are going to convert that equation to rewrite that equation to its exponential form. So we have the base 2 to the power of log, which is 4, equals argument. Argument is 4x plus 6. They are equivalent, okay? They are equivalent. So we have that exponential form. We have that equation written right now in the exponential form. Solve for x. 2 to the power of 4, 16. 4x plus 6. Solve this equation. -6, -6. Cancel. 16 minus 6, 10 equals 4x. Divide by 4, divide by 4. Cancel. X equals 2.5 or 5 halves, right? 5 over 2. And do not forget to double check. Do not forget to double check. When we solve equations, we should always do the double checking. 5 over 2, plug in here. X equals 5 over 2, or 2.5. 2.5 times 4 is 10. 10 plus 6 is 16. Log with base 2 of 16 is 4. Okay, perfect. That's the answer. Okay, that's the answer. This is the answer. Next, question number 4. Write the expression as a logarithm. Write the expression as a logarithm of a single expression. Assume the variable represents a positive number. Okay, basically it's telling us condense. One word. This is to condense the expression. Okay, we have 1, 2, 3, 3 logs with the same base. Oh, actually I see there's a parenthesis here. So, okay, so let's deal with whatever inside the parentheses first. Inside the parentheses, we have an addition of 2 logs with the same base. We are going to use the product rule. Log with base b x with base b of x plus log with base b of y equals log with base b of x times y. So the single log whose argument is a product. That's where the name comes from, product rule. Product rule. So we can write the parentheses, inside the parentheses, log with base 4 of 4 plus log with base 4 of b, that's b, right? As log with base 4 times b, 4 times b, 4 times b. Multiply the 2 arguments together, all right? And continue. We can actually, now we do not need the parentheses anymore. LOG with base 2 times LOG with base 4, 4b, minus LOG with base 4 of 2. Keep condensing. We need to take care of these two. By the power rule, we could move the 2 back inside the argument. Okay? The power rule LOG with base bx to the power of r equals r times LOG with base bx. So if we look at it from right to the left, if we have a coefficient, we can bring it back on shoulder of x. So that's what we're gonna do in this case. Keep the base 4. Original argument is 4b. Now we're gonna put a 2. We're gonna square, put a 2 on the shoulder of the 4b. And then minus LOG with base 4 over 2. All right? Now we are looking at a difference of 2 logs with the same base. So we're going to use a quotient rule. We actually use all the 3 rules for this problem. LOG with base x, base bx minus LOG with base by equals LOG with base bx over y, quotient rule. So we're going to keep the base 4. The argument of the single logarithm is going to be a quotient with numerator 4b to the power of 2, denominator 2. Okay, I can use the color scheme to show you. LOG with base for green minus LOG base with base for yellow. By the quotient rule, we're gonna have LOG with base for green over yellow. Okay, green over yellow could be simplified a little bit more. Let's do that here on the scratch paper. 4b to the power 2 over 2. 4b over 4b squared is just the 4b times 4b, right? 4 times 4 is 16, b squared over 2. 16 divided by 2, 8. 8b squared. So after we simplify, the argument is 8b squared. And that's the answer. One single logarithm. That's condensing. Keep going. 32, we have 18 minutes. Number 5, use the laws of logarithms to rewrite the expression. Oh, this is to expanding. In a form that no logarithm of a product, quotient, or power. So this is expanding. Expanding. All right. Let's analyze the structure of the argument. What I see as a product. The argument is a product. So we're going to use a product rule. We are going to write LOG with base 3, green times yellow as LOG with base 3, green, plus LOG with base 3, yellow. Yellow is that cube rule y to the power 8. Okay, the color scheme will help you to understand. We applied the product rule. When the argument is a product, we can rewrite that log as an addition of 2 logs. Green goes here, yellow goes there. And keep going. I'm going to copy this first log and then rewrite the yellow part, cube rule of y to the power a as y to the power a over 3. Yeah, when did you learn this formula? Foundation 2, did you learn this? Radical. So mx to the power n equals x to the power n over m. So those two expressions are equivalent. And the left is the radical form. This is the exponential form. Same expression in two different forms. Yeah, when did you learn this? You need to know anyway, because in this case we use it. So use this formula. We're gonna write 3 under 8. We're gonna write y, the yellow part as y to the power of 8 over 3. We're gonna write a radical expression in its equivalent exponential expression. Okay. Now let's look at both logs. Their arguments are powers. So we are able to bring the exponent in front of the log. We have 14 log with base 3x plus a over 3 log with base 3y, and done. That's the final answer. We can't expand more. That's it. The expression has been expanded as much as we can. That's the final answer. Did you guys have learned this formula in Foundation 2? Guys, did you learn this one?
Yes.
You did? Okay, in Foundation 2, right? Okay, very good, very good. So that's question number 5. Number 6, find the time required for an investment of $5,000 to grow to $8,900 in an interest rate of 7.5% per year, compounded quarterly. This actually is a Foundation 2 problem. We learned compound interest in Foundation 2. Formula. If you email me, request information about compound interest, I have a good material. I can email you that. So formula for compound interest, P equals, okay, we use this notation actually. A equals P 1 plus R over N to the power of NT. I don't know if you remember this formula. When the interest is compounded not continuously, like a few times, a finite number of times a year. Let me explain the meanings for those variables. P principal. P is the principal. P is the initial principal, right? Principal is the original money you deposit in an account. Originally. And R is the annual interest rate. T is time in year, very important, time in year. If you do 18 months, T is 1.5 because 18 months is 1.5 years. So T has to be in year. N here is the number of times the interest is compounded per year. Okay. If the interest is compounded annually, once a year, N is 1. If the interest is compounded semi-annually, twice a year, N equals 2, every 6 months. If the interest is compounded every quarter, 4 times a year, quarterly, N equals 4. If the interest is compounded every month, 12 times a year, monthly, N equals 12. If the interest is compounded by day, every day, daily, N equals either 365 or 360, depends on the bank. Okay. In this case, P is find the time required for an investment of $5,000. So in this case, your investment is $5,000. Your P is $5,000. To grow to $8,900. Okay. A, what is A? A is accumulated balance. A is the initial accumulated balance. So we use A. You can understand A as the future value of the account. So you're putting in $5,000 and then you wanted to have $8,900 in the future, right? Because the purpose you deposit your money is wanted to have the interest, right? So your P is 5,000, your A accumulated balance in the future, accumulated balance of the account in the future is 8,900. Rate R is 7.5%. R is 7.5%. As decimal, 0.075. Compounded quarterly, N is what? Can you tell me? If the interest is compounded quarterly, what's the value of N, the little n?
4.
Yeah, exactly. So 4. And look at the formula. We have A, we have P, we have R, we have N, we have N here. We don't have T. So T is the variable we are trying to solve. Since T is unknown, T appears in the exponent, the equation is going to be an exponential equation. So this is an exponential model. Growth is a growth. Okay, so let's plug in those values. Formula A equals P 1 plus R over N to the power of NT. A is 8,900. P is 5,000. 1 plus R is 0.075 over N, which is 4. Okay, and then to the power of 4 and 4, 4t. That's the equation we are going to solve. That's the equation we are going to solve. Okay. Firstly, as we see on the right, we basically have two parts multiplied together, right? The first part is 5,000. So I'm going to divide each side by 5,000. Cancel. Then we have, yeah, obviously we can cancel the two zeros here. We have 89 over 50. Not reduced, but actually it's kind of reduced. Yeah, 89 over 50 on the left side. And on the right side, we have 1 plus 0.075 over 4 to the power of 4t. Okay? Yeah, we are solving for t. And we are going to apply the second method. We're going to apply ln on each side. Okay? On the right side, this is the exponent in the argument. By the power rule, we can bring the or move that exponent in front of the log. Then we have ln 89 over 50 on the left side. And we are going to have 4t times ln 1 plus 0.075 over 4. If you want to do 0.075 divided by 4 and plus 1, you are welcome. Okay, this is definitely just a number. Okay, you can evaluate it and put it there. I'm gonna just keep it and then later enter in a calculator. So modify a little bit more on the right side. 4 times t. We can just put a 4 times ln and then times t, right? Yeah, basically, yeah, 4 is a constant, and this part is also constant. 4 times that constant times t. So the whole thing here is the coefficient of t. We are going to solve for t. Isolate the t, divide each side. We run out of space. Divide each side by that. We have t equals ln 89 over 50 divided by 4 times ln. You know, maybe it's a good idea to just figure out what's this. If you feel like that is overwhelming, let's just figure out what is that. Should be very simple thing to do. Use a calculator. I'm going to use my scientific calculator. You will be able to see it, but I will enter the value there. 0.075 divided by 4 plus 1 is 1.01875. 1.01875. So it is 1.01875. Double check. Yeah, we should actually evaluate that part. Otherwise, it's just a very long thing. Where's my calculator? Right here. 1.01875. 1.01 is okay, very good. And that is the t, right? That's the t. We're gonna enter that to the calculator. Let's see the requirement. Rounding or exact? Okay, round to 2 decimal places. Okay. Take a picture of the expression. Numerator ln 89/50. Denominator 4 times ln 1.01875. And it's good because this is just a number that is a finite decimal, so we did not round. We did not round it, so we will not affect the final answer. Let me stop share the note and go to share our calculator. Clear. So I'm gonna do ln. This log. I'm gonna ln. The argument is 89 divided by 50. Close the argument. That's the numerator. Okay, you don't have to do both, like the whole expression. You can do the numerator and then divide by the answer from the first step. Divide by the denominator, which is 4 times ln 1.01A75. 1.01A75. Close the argument. Done. Hold on. Doesn't look like right. Something went wrong here. Let me look at it. You want 8900, so 589.50. 1 plus so it's 1.01875 to the power of 4t. Let me try this. ln or 89/50 divided by a parentheses 4 times ln 1.01 1.01875. Close the argument, close the denominator. Oh, this one looks good now. You know, the mistake earlier is I did not have these parentheses. We should have put the parentheses to frame the denominator. Those are coming from experience. People make mistakes, and the more you see those possible errors, and the better you can do in the exam, because you would be able to avoid it, right? Yeah, earlier, if I do not have these parentheses, the calculator think I'm gonna divide by 4 and then multiply this thing. That's the reason I get a very small number, and the number does not make any sense, right? And this number makes sense. In year, how many years? Let's see the rounding instruction. It says rounded to 2 decimal places. So you're gonna enter 7.76 years. 7.76 years, okay? Let's go back to note. The time that requires to have that much growth is 7.76 years. 7.76 years. All right, I think we can stop here. We've did 6 problems that would really help next Tuesday, that we can finish all the review on time. All right, guys, let's see. We have Kaida, Eliza, Ether, Max, Michael, 5 participants. I'll mark your attendance in a moment. Thank you guys for coming. I'll see you on Tuesday. Feel free to email me if you have any concerns, questions.
Thank you. See you on Tuesday.
Thank you.
Thank you for coming. I'll see you on Tuesday. Bye-bye.